report, which is in progress. This is a joint work with Simone Marchese, who is here, and Juan Pons Lopez and Zhang Valles. So first, let me briefly explain the definition and some history about this object. So first, I'm going to introduce the definition and some history. So I'm going to fix our X to be smooth projective variety. Of dimension n is to 2. And I'm going to fix our base field to be the field of complex numbers. And then inside X, we're going to consider a fixed, reduced, and effective divisor, say D1 plus blah, 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 D sub M. So this is reduced and effective divisor with each di is irreducible. Okay, and then one can define something called the logarithmic tangent shift. As a subshift of the tangent bundle, which fits into the following exact sequence. So Tx is the tangent bundle of X, and so the shift we're considering has the co-corner, which is the Jacobian of the divisor, restricted to D and then twist by D. So basically this is defined over an open character subset U as the set of derivation whose evaluation for the local defined equation for the divisor D. So here Phi is the defined equation. Defined equation for the divisor D inside the open subset U, and this derivation is contained in the ideal generated by this defined equation. So this is how we can define this subshift that is called logarithmic tangent shift. And by definition, we can see that this shift is reflexive. Sorry. This is reflexive. So in particular, if we consider projective surface and its divisor, its logarithmic tangent shift is in fact locally free. And also we can consider its dual shift, which is also called logarithmic shift or logarithmic cotangent shift. So omega x 1 log d is defined to be the dual of the logarithmic tangent shift. So again, this is reflexive, and also on surface, this is locally free. And I have to mention that this is originally introduced by Deligne for the case when the divisor has simple normal crossings, and later it is generalized to arbitrary reduced and effective divisor by Kyoji Saito. Okay. And another remark is that even for higher dimensional smooth projective variety X, if the divisor D is a simple normal crossings, then this shift is always locally free. So logarithmic tangent shift, sorry. is always locally free. And in this case, the co-corner, the Jacobian restricted to D and twist by D is in fact the direct sum of the normal bundle of each irreducible component. Okay. And in this case, if you take the dual of this exact sequence here, if you take the dual of this exact sequence, we can get the following exact sequence for logarithmic cotangent shift. Which is called the Poincare residue sequence because the map from the logarithmic tangent shift or tangent bundle to this co-kernel is called the Poincare residue map. So this map is called Poincare residue map, which is defined by locally sending the following section, ui d log ci plus sigma ui d ci, where I runs from 1 to k, and the second sum is for I from k plus 1 to n, and where here z1 blah 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 zk equals 0 is the local defined equation for the divisor. It is a local equation for the divisor D. So that means since we assume that our divisor has simple normal crossings, so that locally this local equation can be expressed as the coordinates z1 to zk, and it extends to the whole coordinate z1 to zn. So locally, our logarithmic shift is defined by this section, and then this is mapped to the evaluation of u1 through uk at x.
Oh, excuse me.
Yes.
K is M or?
K is, yes. No. Oh, sorry. Since we assume that it is simple normal crossing, yes. So in this case, yes. If D has just a normal cross.
You're on an open subset.
Yes. So locally, this residue map is defined by this.
You mean K is not equal to M? Different.
No, because globally there are M components. But locally,
local.
okay.
Okay.
Okay. Are there other questions? Okay, so this is a brief definition for our object in consideration. And let me talk a little about some simple example. So let's assume that our variety is projective space with dimension n and needs to 2. And then our divisor, let's assume that our divisor is defined by a homogeneous polynomial of degree, say, d. Right? And then we can define a surjection from, so here S is the coordinate ring, polynomial ring in n+1 variables. And we can define a map from here to the Jacobian by the partial derivatives. Round 0, f, blah, 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 round n, f. All right. And then we consider its kernel. Usually we denote this by this notation, right? And then the simplification of this module turns out to be our logarithmic tangential.
Oh, excuse me.
So for example, yes.
What is it? S1? S1 or what?
Sorry, S is the polynomial ring for this projective space in n plus one variables. So we just how to say, twist, shift by one. All right. So for example, if f is a polynomial degree n plus one, defined as the product of each coordinate x0, x1, blah 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 xn, then we can obtain the following exact sequence. So in this case, this corner module turns out to be the n copies of polynomial ring. Where if you denote this, if you say that this map is defined by a matrix, n plus one by n matrix, then this matrix is simply given by the following form. So here we have x0, x1, blah, 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 xn minus one. The last row consists of just minus x sub n. Right? So that from this, you can simply simplify this free module. Then you see that our logarithmic tangent bundle is nothing but the direct sum of n copies of OPN. Okay. And more in general, by the same idea, for divisor D, whose irreducible component is hyperplane, H1 say to H sub m, where m is at most m plus one in general position, which means they have simple normal crossings. Then, similarly as before, we can observe that logarithmic tangent shift or tangent bundle is isomorphic to O1 n plus 1 minus n copies n O. Yes, n minus 1 copies. Okay. Okay. And just the one comment is that if the divisor, in this particular case of hyperplane arrangement, if they do not have simple normal crossings, for example, if our divisor is 3 lines in P2 with a triple point defined by, for example, x0, x1, and x0 plus x1, by the same argument as before, we can see that the logarithmic tangent bundle in this case, although this does not have simple normal crossings, since we are talking about P2, so every reflexive sheaf is locally free. So this is vector bundle. So this is, in fact, the direct sum of 2 line bundle with degree 1 and degree minus 1. So this logarithmic tangent bundle, we can see that heavily depends on the dual lattice of the hyperplane, or how, in general, how they intersect each other. So the natural question can arise from this simple observation that here in this case of a hyperplane arrangement, we see that for any such arrangement, the corresponding logarithmic tangent bundle is invariant. It stays the same. So that means, so that raises natural question, for which divisor, the corresponding logarithmic tangent bundle characterize the divisor itself. So that question is called the Torel question. And that is the one we are interested in. So if for two divisor D and D prime, whose logarithmic tangent bundle or tangent sheaves are isomorphic to each other, then when can we say that D and D prime are same? So here I'm saying that same, not equivalent. And in that direction, there are many works done. And let me just mention some of them. First one is by Durgachev, Kapranov, and separately by Valles. It says the following: for the divisor whose irreducible components are hyperplane, so we can simply call it hyperplane arrangement with simple normal crossings, and the number of hyperplane is at least n plus 2, then we have Torelli property. If and only if the divisor D does not oscillate any normal rational curve in Pn.
You mean X is Pn?
Yes, sorry. So here, X is always Pn. Thank you. And the next important result is by Yoshinaga and Ueda. Here they consider smooth divisor in Pn again. Then they show that we have Torelli if and only if the defined equation F is not of Sebastiani form type, not Sebastiani form type, which means you cannot divide the collection of variables into two parts so that F cannot be written as G plus H, where G is expressed as G is expressed in terms of certain collection of variables, and H is expressed in terms of the other variables. So if you cannot separate these variables, then we say that F is not of Sebastiani form type. And that happens if and only if we have Torelli for the corresponding logarithmic bundle. Okay. Right. And let me make one comment. Actually, this definition of the logarithmic tangent sheaf and logarithmic cotangent sheaf are by Delin and Saito, and there are other versions of logarithmic sheaves or logarithmic sheaves. As far as I know, there are two such. I'm pretty sure that I'm not sure whether they are all possibility, but as far as I know, there are two other versions of, let's say, their refinements of logarithmic shapes, cotangent shape. I will denote them by omega x tilde log d. And this is a subshape of the logarithmic shape by Delin. And also there is another refinement, subshape of this tilde, say double tilde. The first one is by Fabrizio Catanese. Second one is by Durgachev. And I'm sticking to the notation of the Dolgachev for his shift, but for Catanese, this is not the notation he used. What he used is just the usual notation for the logarithmic shift, but to distinguish, I will use just double tilde. The thing is that here, there is, if you consider Poincare residue exact sequence, there is a surjection from the logarithmic shift by the lin to x1 Jacobian to Jacobian OX. And in fact, Dolgachev, the Poincare residue sequence, has a surjection from his logarithmic shift to the direct sum of u star O di prime, where u and u as a map from di prime to di is the resolution of the divisor d. So here, recalling that our divisor for the logarithmic shift is just the reduced and effective divisor. We don't have to assume that they are simple normal crossings. So in general, each di doesn't have to be smooth. And for Dolgachev's logarithmic shift, we have a surjection to push it forward via the resolution of each irreducible component. But instead, for Catanese, we have just the direct sum of the structure shift of each component. So that's the difference between these two logarithmic shifts. And in fact, when we consider Dolgachev's version or Catanese version, since they are refinement of the logarithmic shifts, they have more information about the divisor. So we can say that it is easier to get positive answer to the Torelli question for the refinement. Right. For example.
Oh, excuse me. So for
yes.
normal crossing divisor, they are all same?
For simple normal crossing, they are same. For normal crossing divisors, with some extra condition, then Dolgachev's notion is same as the Delisle's notion. So for example, if you consider the plane nodal cubic curve, so this has normal crossing. So in this case, Dolgachev and Delisle's notions are same, but Catanese's notions is different. So for example, if you do some computation for this Dolgachev and Delisle's notions, so this is they are isomorphic to each other. And in fact, this is a stable vector bundle on P2 with first chunk class 0, second chunk class 2. So that its set of jumping line forms a smooth conic in P2, and by the result by Barth, that set of jumping line determines the corresponding vector bundle. So we have 8-dimensional family of nodal cubic curves in P2, but the set of smooth conic forms a 5-dimensional space. So certainly we do not have Torelli. But if you consider the Catanese's logarithmic shift, we still don't get Torelli. We still get the negative answer to the Torelli question, but it has the information about this singular point. Right. So logarithmic shift by Dolgachev and Delisle are locally free in this case, but Catanese's one is not locally free. It's a singular at the singular point. So yes, so you have an idea that we get more information about the divisor from the Catanese's logarithmic shift. So we can get more positive answer. We can expect to have positive answer to the Torelli questions. Okay, so this is a brief definition and history about the logarithmic shifts and Torelli questions. So if it is okay with you, I will move on to the next section, which is about our recent result. So I should say our approach. Approach number 1. So basically, our approach is to add extra condition to the divisor. So even when we don't have positive answer to the tutorial question, our idea is to add some extra information to the divisor, and then we'd like to get some positive answer to the tutorial question. Okay, and for that strategy, for that approach, let me introduce our key lemma. Here we consider the same situation. X is a smooth projective variety of dimension n mixed 2, and we assume that our divisor D has simple normal crossing, so that the corresponding logarithmic shift is locally free. And we fix a smooth curve C in X. Smooth curve. Let's say C intersect with D at points PI's with multiplicity AI. I's from 1 to say T. Okay. Then we can expect to have the following commutative diagram for points B, zero-dimensional scheme B, DI, PI, where I runs from 1 to T, and PI is either 0 or 1. The commutative diagram is formed as follows. First, we restrict the Poincare residue sequence to the curve C. So Tx minus log D, 2, Tx2. Here we have Jacobian D, and then we restrict to C. Since D has simple normal crossing, the co-corner is nothing but the direct sum of the normal bundle of each reducible component. And then we consider tangent bundle of the curve C, and then its co-corner is the normal bundle, right? If C intersect with D transversely, we can have the following. So here we have, the same thing here. And here we have TC, logarithmic tangent bundle minus log C intersection with the D. And then we have from here we have injection, and the co-corner is nothing but normal bundle of C, right? So this is what we can expect when C intersect with our divisor D transversely. But in general, if AI for some I, AI is at least 2, so that they do not intersect D, it does not intersect D transversely, then we can have the following commutative diagram. So here. We have OB. Here we have OB prime. So OB prime is the residue. So basically, let me rewrite this. So this will be sigma O DI restricted to C, right? So this is simply C intersection with the D, and then we take B, so B prime is the residue of this, B inside the C intersection with the D, and then we have something as the corner for the surjection from the normal bundle to OB prime, and that corner is denoted by, we denote it by log D with respect to B. We have this commutative diagram for this points B if and only if all the bi is equal to 1. B is just the sigma pi. That means any bi is equal to 1. That is if and only if condition. Okay. And it turns out that this lemma is really powerful, very useful in distinguishing one logarithmic bundle from the other. And here is an example.
What is B prime?
So we have we can simply, okay. So B prime
Yeah.
is the sigma AI minus BI times PI. Yes. Yes. So for example, let's consider plane and a smooth conic. On P2. And then let's consider the tangent line to this conic. Right? So that means the intersection of these two curves is 1 point with the multiplicity 2. So here we have just the 1 point OP. This is the intersection of the tangent line with the smooth conic. So this is O2P. And here we have OP. And then normal bundle is OP1, 1. And then here OP1, 2. So here this should be OP1, 1. Here we have OP1. So logarithmic tangent bundle of this smooth conic restricted to this tangent line, log restrict to C is OP1, 1 plus OP1. And also similarly for non-tangent line, we can observe that they have the same splitting type. So our logarithmic vector bundle is uniform with the splitting type 1, 0. And it turns out that you can easily exclude the case when this is a direct sum of two line bundles. So this is equal to isomorphic to omega twisted by 2. So in particular, the smooth conic is not totally. Okay. But the thing is that, so our idea is to blow up a point not contained in this conic. So let's consider blow up pi x, which is a blow up of P2 at one point, say P, where P is not contained in this smooth conic. And then let's consider line passing through this point P, and then consider just strict transform, say C. So C is in the system of XL minus E, where E is the exceptional divisor and L is the pullback of the line. Okay. Then apply this key lemma to the logarithmic tangent bundle associated to the strict transform of D. So let me write it down. So we consider logarithmic tangent bundle of D tilde, where D tilde is the strict transform of D in X. And then we restrict this logarithmic tangent bundle to C. Then it turns out that we have two different splitting. First, we have direct sum of two copies of O if this C intersect with the transform D tilde transversely. Intersect D tilde transversely. And if it is tangent to D tilde, we have different splitting type. C tangent to D tilde. All right. And so that means if we blow up many points, for example, 3 points, then we can characterize our conic from these exceptional curves, C, because if you have 3 points at which you blow up, then at each point there exist 2 lines which are tangent to the strict transform, which characterize the logarithmic tangent bundle, at which we have different splitting type. So we get the following proposition. So it is true for 3 points of blow up, but for later use, let me blow up at 6 points. So let's consider smooth cubic surface S obtained by blowing up P2 at 6 points in general position, say Z, right? It's a smooth cubic with Z is 6 point P1 to P6 in general position. Then we have Torelli for omega S1 log D with D from 60, smooth 60. Okay. So our main philosophy is that even when we do not have positive answer to the Torelli question, we just blow up our base space at points outside the divisors. Then eventually upstairs, we can expect to have Torelli, mainly because of this key lemma, the commutative diagram appearing in this lemma. And in fact, we can obtain the following proposition. We have Torelli for this logarithmic bundle. In fact, this logarithmic bundle is stable, so that there exists genetically one-to-one map from the linear system, which is P5, to the moduli space of stable bundle with respect to the hyperplane section. So this is minus Ks. So Ks first chunk class is Ks plus 2L, second chunk class is 7, sending D to the corresponding logarithmic bundle. Okay, so let me briefly explain the main idea. And in fact, the idea heavily depends on our key lemma about the restriction of the logarithmic bundle or tangent bundle to the 2 curves. So if you assume the sub-bundle, existence of sub-bundle, log D, then the slope with respect to our polarization of this bundle is 3/2, right? So for example, and so that means by restricting our sub-bundle to several curves, we try to obtain contradiction if the slope of the line bundle is at least 3/2. So for example, if line bundle is minus 3L plus 2 times sigma EJ, right? Then
what is S
sorry.
and what is L? Here, what is S and what is L?
Sorry, S is a cubic surface, sorry. I'm using the same notation used in this proposition. And L is the pullback of the O1, OP21.
Okay, thank you.
And then first, we can obtain the following exact sequence: OS minus 3L plus 2 sigma EJ, omega S1 log D, and ideal shape of a point twist by 2L minus sigma EJ to 0, right? That means we can assume that this line bundle is saturated, and by applying our key lemma to exceptional divisor, each exceptional divisor, we can conclude that the point P here appearing in this co-corner is not contained in any exceptional divisor, right? There we used our key lemma. Second, we can also show that P is not contained in any LJ hat, where LJ hat is the strict transform of the conic downstairs passing through every segment except PJ. So that's from OS to L minus sigma EI plus EJ, right? And we can also, using our key lemma, we can also show that the intersection of LJ hat with the divisor D is in fact 1 point with the multiplicity 4. So our downstairs in P2, our D is a conic, smooth conic. LJ hat is also another smooth conic, intersecting each other at only at 1 point with the multiplicity 4. That's true for any J. Sorry?
You said not in.
Sorry, you're right. This is not contained in LJ hat. Thank you very much. Right? And also, so because of this second step, we can guarantee the existence of the unique smooth curve, say C or C1, 2, 3, 4 in IP 2L minus E1 minus E2 minus E3 minus E4. So there exists the unique conic passing through P1, P2, P3, P4, and P. And then if you apply our key lemma to this curve C, we see that the splitting type is 3 and minus 1. And also, it intersects with the D at only 1 point with the multiplicity 4. And by changing the index, we can find many such curves, I1, I2, I3, I4, for I1, blah, 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 I4, and most of 6. But here we have fixed conic D or pi D downstairs, right? And then if you think about the family of conics which intersect this conic at 1 point, only at 1 point with the multiplicity 4 is parametrized as follows. So that is given by considering a point in this conic and consider the line with the multiplicity 2, and then you consider the pencil spanned by this conic and this double lines. That's all. That's all possibility for the conic whose intersection with this conic pi D is just 1 point with the multiplicity 4. That is simply, if you consider the family of conics P5, here we have a point parametrizing our conic pi of D. And then here we have barometer surface. And inside barometer surface, we have a curve parametrizing the tangent line to this conic with multiplicity 2. So that means such conic intersecting pi D at only at 1 point with multiplicity 4 is parameterized by the cone over this curve inside the barometer surface with vertex point. So it is surface of degree 4, right? Now, if you fix I1 to be 1, so that means our smooth conic is passing through P and P1, right? So that is parameterized by P3 in this P5. So that intersect with this cone at most at 4 points because this is degree 4. So we have So that means we can have at most 4 such conics. By such, I mean the intersection with this fixed conic D is just 1 point with the multiplicity 4. But here we fix I1 to be 1. So we have freedom for I2, I3, I4. So we have 5 choose 3. So we have at least 10 such curves. So that's contradiction. So we can get contradiction for the existence of such line bundle inside the logarithmic bundle. Similarly, we can exclude all the other cases. So eventually we can show that this logarithmic bundle is stable. Right? And similarly, we can also conclude that there exists genetically one-to-one map from the family of the lines P2 to logarithmic moduli space with the first term class KS plus L. Second term class is also 7. Recall that the corresponding logarithmic bundle associated to line, single line, is just the O minus direct sum of 2 copies of O minus 1. So it does not, we do not have totally property. And for smooth conic, we have the twisted tangent bundle of P2. So in particular, we do not have totally. But here, after blowing up at 6 points, we have totally positive answer to the totally questions. Okay, so this is our first approach. And our second approach is not the second approach is to consider everything downstairs. So somehow in the first approach, we consider upstairs after blowing up. And second approach, we try to move everything back to downstairs by applying the push it forward. So for example, upstairs, we have this Poincare residue sequence, omega S1. Again, S is a cubic surface, omega S1 log D. And then we have OD. Assume that D corresponds to conic, smooth conic, passing through P1, P2, P3. And in fact, by considering different sixers defining the blowdown, this corresponds to the lines in P2 via the different blowdown. Now we apply the push it forward functor to this exact sequence. Then we get that we can obtain that by applying the formal function theorem, push it forward of omega S is omega P2. And then we have push it forward. And then we have conic through 3 points. And then we have higher direct image of omega S1, higher direct image of omega S1 log D, and then 0. And applying the formal function theorem, we can see that this is a direct sum of OPI, where I runs from 1 to 6. So here PIs are the points at which we blow up to get smooth cubic surface. And this turns out to be the direct sum of OPI, where I runs from 4 to 6. So from this, we can get the following exact sequence, short exact sequence. Omega P2 to the push it forward. And then we have ideal shape of 3 points in the conic minus Z1, 2, 3, where Z1, 2, 3 is P1, P2, P3. Okay, so the question is, can we still expect to have totally positive answer to the totally question for this flow down, for this push forward? So the question is, do we still have totally for this push forward as D runs over the system 2L minus E1 minus E2 minus E3. So as D runs D for the smooth conic in P2 through 3 points, so that's parameterized by P2, can we still have totally positive answer to the totally question? And the answer is yes. In fact, there exists genetically one-to-one map, say phi from the system, linear system, P2, to moduli space of stable bundle in P2 with rank 2 first chunkless minus 1 second chunkless 4, sending D to star pi lower star omega S1 over D. So that means first we have positive answer to the totally. Second, push it forward is stable, and so on. And in fact, we can say more. And the step goes as follows. First, we can get that, before I said that we need only 3 points to get positive answer to the totally for smooth conic. So here we use 3 points, P1, P2, P3 contained in the conic. We have the other 3 points, P4, P5, P5, P6. So from these extra blob at these 3 extra points, we can get totally as before. So the problem is that how can we get stability? And in fact, from our exact sequence here, we can show that our sheet push forward admits the following resolutions: OP2 minus 3, 3, P2 minus 2, 5, and push forward. So that is called a Steiner resolution. So that makes us to conclude that our push forward is stable. And chunk classes are -1 and 4. And in fact, we can say more. For example, let's consider another divisor, D, original divisor D, plus the corresponding exceptional divisor E1, E2, E3. Because here we have D, pi D, downstairs, through 3 points, a blow-up P1, P2, P3. Upstairs, we have E1, E2, E3, and then D. So the sum of these 4 is our new divisor, D prime. Then we can get the natural map from the pi pullback of logarithmic bundle associated to conic, which is the twisted tangent bundle, to logarithmic bundle upstairs, log D prime, which is injective because our pullback is locally free. And then we can consider its co-corner. It turns out that this co-corner is just the direct sum of OEI twisted by -1, where I runs from 1 to 3. And then we take the push it forward. By taking push it forward, then we can get isomorphism between the push forward of the first and push it forward of the second, which is tangent bundle twisted by -2, right? And then we consider the Poincare residue sequence upstairs, omega s, modified Poincare residue sequence, omega s1 log d prime, direct sum of OEI to 0, where I runs 1, 2, 3. And then we apply push forward functor. So the first one is what we want to consider. Second one is second one was shown to be the tangent bundle twist by -2. And then the last one is just the direct sum of OPI, where I runs from 1 to 3. And then it goes to 0. So in particular, our push forward that we are considering is non-locally free. It's not locally free. And its double dual is the logarithmic bundle associated to the smooth conic downstairs. And its a singular point is the point at which we blow up, contained in our conic. Okay, so that's some extra information that we can obtain. And moreover, sorry, I forgot to say, this omega S1 log D have Torelli property upstairs, but to show the positive answer to the Torelli question downstairs, we need more. So that's our key part. We consider the set of jumping lines for this push forward. In fact, this set of jumping line consists of 6 lines. The triangles, the 3 sides of the triangle, P1, P2, P2, P3, and P3, P1, and then the tangent line at each vertex of this triangle. And tangent line at P3. So we can recover our conic from this information about the set of jumping lines. Okay. And so that means we can still get the Torelli positive answer to the Torelli question downstairs. So that's our second approach. And based on this example, we reached the following definition. So please give me more minutes, just a little. So let's consider reduced and effective divisor with simple normal crossings, D1 plus blah, 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 Dm with simple normal crossing inside surface. And then pick finitely many points on the smooth part of the divisor. And then consider the blow up of X at these points, say X tilde, right? And then consider the strict transform of this divisor. Then we can get exact sequence as before. ODJ minus CJ to 0, where J runs from 1 to M, where ZJ is intersection of Z with DJ. So ZJ is the part of Z containing DJ, right? So we have this. So from this, we define logarithmic shear associated to the pair of divisor and points where Z is containing D to be the push forward of the logarithmic bundle upstairs. Then we can see that this is not locally free. and its double dual is the logarithmic bundle associated to D, and its a singular point is exactly the points in Z. So this is what we call generalized logarithmic shift. Associated to pair. And that's all I prepared to speak today. Thank you.
All right, thank you very much. So any questions and comment?
Oh, excuse me.
Yes.
If the Torres theorem is the complement of the divisor gives a different mixed structure.
Yeah, I mean, they say that this is introduced by Delane to construct the mixed structure on the, yeah, but I'm not really familiar with this story.
So even D is not, if you Torres theorem says D is not equal to D prime, then the complement has different mixed structure. Is true or not?
That, as I said, I don't know.
Okay.
I don't know. I mean, certainly here in this meeting, I can see many names who are much more experts than me about this topic. Sorry.
Oh, okay, thank you.
Okay, any other questions and comment? All right, let me ask one thing. So in your last proposition, so the map is still regular, right?
Which one?
This one, this proposition, you just dotted. I mean, when you stated this proposition, so you just dotted, but it's regular, right?
This one?
Yeah. So this map is still regular.
No. This is not a morphism. I mean, certainly there are.
So every D is the. I think a D is always effective and reduced. In this case.
Certainly what we showed is that this pushes forward the logarithmic bundle associated to smooth conic through P1, P2, P3 is stable and with these chunk classes and so on. But if our D is not smooth, so that it has more than one irreducible component, say, for example, L minus E1 minus 2 plus L minus E3, for example, then the corresponding logarithmic bundle has different chunk class.
Okay, sorry.
So if you deform your divisor, then the corresponding logarithmic bundle can have different second chunk class.
Okay.
So, and in fact, so because of this observation, using this kind of argument, you blow and then we push it forward. We try to define a new version, new kind of the logarithmic shift, which has the same, like this kind of numeric invariant, if you deform it.
Right.
That's one of our recent work in progress.
Any other questions and comment? Okay, if no more, then thank you very much. So let's thank the speaker again. Thank you. And for everybody, thank you for coming, and you have a good day. So, all right.
Also, I'd like to thank you all very much for your patience. Thank you.
All right, thank you. It was very nice talk. All right. So have a good day.
Have a good day.
Close this room. All right. So bye.